Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Welcome to section 2.3. The title of this section is State Space to Transfer Function. In this section, we will learn how to convert from a given state space to a transfer function. Upon completion of this section, you should be able to convert a given state space equation to a transfer function. Prior to watching this video, you are required to do self-revision on the following. First is how to multiply matrices. Second is how to invert a matrix. And third is how to use calculator to perform matrix operation. I have included several YouTube links for your references. And for better understanding, try to answer self-revision exercise shared through Telegram channel. Firstly, we will derive the conversion equation for state space to transfer function. As we have discussed in the previous video, state space representation consists of state equation and output equation, and it is in time domain. To convert it to a transfer function, which is in S domain, we need to find its Laplace transform. Again, using the differentiation theorem, item number 7 from the Laplace theorem table, Sxs is the Laplace transform of x dot term in the state equations. Overall, equation 1 is the Laplace transform of state equation, and equation 2 is the Laplace transform of the output equation. Rearrange equation 1 by taking Axs term to the left side, then factor out Xs. The term S is multiplied with an identity matrix to convert it into a square matrix to enable subtraction operation with matrix A. Then rearrange the equation as in equation 3. Next, substitute equation 3 into equation 2, you will get equation 4. Rearrange it in terms of ys over us, you will get equation 5. This is the equation to be used for state space to transfer function conversion. We will go through an example in the next slide. Let us consider this example. Given to you a state space representations of a third order system where the state equation and the output equation are as given. So you have to convert the state space representation to the transfer function. In the next slide, I will show you step-by-step procedure how to obtain the transfer function. Using the derived state space to transfer function equation highlighted in yellow, the first step is to solve the Si minus A inverse term in the equation. The formula of Si minus A inverse is the adjoint of Si minus A over the determinant of Si minus A. Firstly, find the Si minus A matrix as shown in equation 1. Secondly, find the determinant of Si minus A, you should get equation 2. Next, we need to find the cofactor of Si minus A, you should get equation 3. Then, the adjoint of Si minus A is the transpose of the cofactor of Si minus A, you should get equation 4. Now that we have the adjoint of Si minus A and the determinant of Si minus A, thus we can obtain the inverse of Si minus A shown in equation 5. Now we are ready to solve the state space to transfer function problem. In step 2, substitute the output matrix C and the input matrix C in the equations and multiply the terms accordingly. You should get the transfer function as shown in equation 6. During the multiplications of the matrices, you have to make sure that the dimensions of the matrices are matched. Note that the obtained transfer function is a closed-loop transfer function. For your exercise, I have included two exercises. Exercise 1 is state space representations of a second order system. Exercise 2 is state space representation of a third order system. However, if you look at the input and output matrix, it consists of non-zero values. So it is more challenging than the example that we have discussed. That's all for now. Thank you for watching.